Not every search app needs Elasticsearch. SQLite FTS5 gives you BM25, snippets, and filters in one file-backed Python search engine. You'll learn how the pieces fit into a workflow that indexes documents and ranks filtered, paged results with readable snippets. I'm Professor Pi, teaching search and IR with simple Python. Search often becomes the slow, annoying bit in small apps. You can avoid another running service and still get relevance, highlighting, and simple filters by using SQLite FTS5 inside the same file your app already uses. For many teams, that trims latency, complexity, and ops without a separate search cluster. BM25 is how we score relevance. It favors documents whose words match the query, with a penalty for length. FTS5 gives us a virtual table that tokenizes text, exposes BM25 scoring, and can produce snippets. It's simple and predictable, though it doesn't do distributed scale or the fancy language tricks of a dedicated engine. We'll build a tiny local demo that indexes 3 documents, ranks with BM25, weights title versus body, filters by a stored tag, returns highlighted snippets, and wraps it all in a paged query function. That's the minimal flow to go from raw text to a usable search UI. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's create the index and load a tiny corpus so we have data to search. This snippet creates the smallest useful SQLite FTS5 index and loads 3 searchable documents. Small apps often need real full-text indexing without adding a search cluster, and this keeps the moving parts inside SQLite 3. The virtual table docs has T for title text, B for body text, and tag marked UN indexed, so it can be stored and filtered without joining the full-text vocabulary. db.executeMany inserts the toy corpus in one call, which is the same shape you would use for a small batch loader. The output confirms the index has real rows before ranking starts. Now that rows exist, we need a way to ask for relevance and get the best matches first. This example runs the first relevance-ranked SQLite FTS5 query with BM25 docs. Exact keyword lookup alone is not enough for retrieval systems. You need a stable way to put the best-looking hits first. The query uses docs match S, so the search string stays parameterized, then order by BM25 docs. Row ID sorts by SQLite's BM25 score and breaks ties deterministically. In FTS5, lower BM25 docs values sort as better matches, so ascending order is intentional here. The output shows the best row identifier and title. Proving the index can return a ranked hit. Ranking looks good, but users often expect title matches to count more than body matches. Let us experiment with column weights so results reflect that expectation. This code shows how SQLite FTS5 column weights can change which document wins. Relevance failures often come from treating title hits and body hits as equally useful, even when users expect titles to carry more intent. The 2 added rows make the contrast visible. One repeats ranking in B, while the other has ranking in T. Top 1,8 favors the body column more, and top 8,1 favors the title column more, while the match value remains parameterized. Raising a column weight makes hits in that column contribute more strongly to the ordering. The output shows the winner flips, which is the practical signal that weighting is working. Users also need to see why a result matched and to filter by simple metadata before paging. Let's add filtering and produce a highlighted snippet so the result is explainable. This snippet adds the result presentation layer that search users notice immediately. A ranked hit is much easier to trust when the page shows why it matched. And many retrieval flows also need metadata filters before pagination. The where clause combines docs match R with tag equals X, so the full text condition and the stored tag both constrain the result. Snippet docs 1 row S6 asks SQLite FTS5 for a short body fragment from column 1 with match terms marked. The output shows the filtered title and a compact highlighted fragment, which is the bridge from ranking to usable search UI. Finally, we want a reusable function that keeps ranking, filtering, snippet extraction, and paging consistent across the app. This example packages the SQLite FTS5 pieces into a tiny baseline search function. Retrieval code gets messy when ranking, filters, snippets, and pages are scattered across call sites. So search keeps the query shape in one place. The function builds only a small fixed where variation, keeps user values in args, orders by BM25 docs, row ID for stable pages, and applies limit plus offset. Size controls how many rows each page returns. Increasing it gives the caller more context per request, while decreasing it can reduce work and response payload. The output shows a filled first page and its leading title, which is the minimal zero server search demo. If you take this toy example into a real product, map the tag field to your actual category metadata. Use the same snippet settings for UI consistency, and keep the weight choices as tunable configuration. In a help center search, you might weight titles higher and return a slightly larger snippet for context. In a news archive, you might reduce title weight and prefer body matches. What this is: a compact file-backed search using SQLite FTS5 with BM25 ranking, snippets, and simple filtering. When to use it: for single machine apps, prototypes, or small services where running a search cluster is overkill. One short caution: FTS5 is not a replacement for distributed search when you need high throughput or advanced language features. A practical next step is to tune BM25 parameters by experimenting with K1 and B for your corpus and user behavior, and measure which combination improves click-through on your dataset. Change K1 to control term saturation and B to control length normalization. If short, practical IR helps, subscribe and watch the IR videos.